Swayam Prabha. Digital India. Educated India.
All right, so good morning, good afternoon. Welcome back to our course on analysis and design of rigid pavements. We looked at module 1 when we started the course. That was an introduction to rigid pavements. In particular, there we saw that there are four types of rigid pavements, that is JPCP, jointed plain concrete pavements, JRCP, jointed reinforced concrete pavements, CRCP, continuously reinforced concrete pavements, and finally PCP, pre-stressed concrete pavements. We had mentioned that JPCP are the most common types of concrete pavements, and so for most of the class, we'll be talking about JPCP. CRCP you will find in certain applications, typically those where you have a high volume of heavy vehicles, but their analysis is fairly similar to JPCP. So we'll be analyzing it as a kind of variation of JPCP. JRCP is rarely used, and PCP is used in specialized applications such as airport pavements for the most part. And therefore, we will not be going into any detail about those two in this class. Now, we began Module 2 a couple of lectures ago. Module 2 is the analysis and design of rigid pavements based on classical methods. And I mentioned back then, which I repeat, that classical methods essentially means without computers. So something that you could do a hand calculation, something maybe you could do it on a calculator or on a spreadsheet. But any sort of analysis which has a closed form solution is what we call a classical method. In the previous set of lectures, we started out by talking about what are the classical methods for analyzing JPCP. And we saw there that the basic theory that forms the basis of analyzing JPCP is that of plate theory. In particular, there are different types of plate theory, but we are mainly interested in medium thick plate or Kirchhoff-Love plates. In addition, we also analyze the plates as sitting on what's called a Winkler foundation or a dense liquid foundation. So these two, Winkler foundation plus dense liquid foundation or Winkler foundation plus the medium thick plate theory, together gave us our basic theory for analyzing rigid pavements. And the equation that we use is called the Sophie-Germain equation, which we had derived previously. And then we add a correction to it to account for the Winkler foundation, which gives us the governing equation of JPCP pavements. Now, in the last two lectures, we saw that it's well and good to have a governing equation, but how do we get a solution for those so that we can do our analysis? And I introduced you to Westergaard solutions, which is about 100 years old at this point. Those were the first and most fundamental solutions, which are still used quite widely around the world today, which looked at the critical stresses as well as the displacement in JPCP sections when they are loaded in the interior, when they're loaded in the corner, and when they're loaded at the edges. And I mentioned that at the edges, that's where you have the critical stresses. We also verified this using an example. Then we looked at certain updated solutions for Westergaard solutions. So Westergaard solutions is over 100 years old, and since then many more updated solutions have been developed. So we looked at some of those solutions, and we concluded also by showing that while all those solutions provide somewhat different estimates compared to Westergaard's, and it can be quite a dramatic difference, they all suffer from certain basic deficiencies, namely the fact that they assume that the slabs are essentially infinitely long, in the sense that while there are joints, all the other joints are far away from the joint under consideration. Or if the loading is in the interior, then all the joints are away from the loading in the interior. And that brought us to one point that there seems to be some limitations of all these classical theories that are trying to obtain analytical solutions of the Sophie-Germain equation. We will talk more about that when we get to module 3, when we get to the finite element method in terms of how to overcome those shortcomings. But in today's lecture, what I wanted to talk about, not just this lecture, but in the next two lectures after this one as well, I wanted to talk about one more aspect of JPCP, namely the joints. So Westergaard solutions and all the variations of that we looked at previously, they were concerned with a single slab. But as we know, JPCP sections consists of not a single slab, but you have several slabs which have joints cut in between them. So, what we would like to know is how do we analyze these joints? How do we know whether these joints are performing well? What does it even mean for a joint to perform well? And how can we take advantage of joints to improve our design? So, in today's lecture, I'm going to run you briefly through some of the basics about joints, how we design joints, what is the purpose of joints, and how do joints aid in our in the performance of rigid pavements. And in the upcoming lectures, we will look at some more mathematical theories, still classical theories, in terms of analyzing joints. Okay, so in today's lecture, I will point out what is the need for joints, and I'll particularly calculate and define and calculate a particular term which is called LTE, load transfer efficiency. So let me write that down. So this is load transfer efficiency. And we will see that it is a pretty basic way to characterize joints. It's somewhat empirical, but it is very useful for joint characterization. And finally, we will list the components of joints and talk a little bit about their construction methods. Okay, so as I mentioned previously, that JPCP sections are not monolithic concrete sections. They instead consist of joints, and those joints are put in during the time of construction, primarily because they reduce stresses. So as we saw, as we discussed initially in module 1, and as we quantified actually towards the end of the previous lecture by looking at the paper by Ioannidis et al., we saw that as the size of the slab decreases, the stress in the slab actually decreases as well. Therefore, ideally, we would like to make our slabs as small as possible. However, the problem is, in order to make the slabs as small as possible, we have to physically go in and saw those joints. That process is fairly labor and equipment consuming, it's time consuming, it's expensive. So we cannot saw in very small joint sizes for highway applications. It would start becoming uneconomical at that point. So we try to find something in between, and we'll talk about how we can improve that particular aspect today. So the purpose of having joints in JPCP, first and foremost, is to reduce stresses. But the result is that it leads to an increase in time and cost. So we have to think about how many joints we want. One other issue for joints, which we talked about, which we'll also briefly discuss today, is that they also create a potential path for moisture ingress. So if the joints are not sealed properly, if you don't make sure that they're perfectly waterproof, then it's possible that they provide a path for moisture to ingress from the joint into the base layer or eventually the subgrade layer. And that can cause adverse effects in terms of distresses in the JPCP section. So we'll talk a little bit of how this can be prevented today. Okay, so let's go into a little more detail about construction of joints. Generally, for highway applications, we first lay down a large amount of concrete. Now, that can be done in two ways. It can be done through what is called fixed form paving, which, as the name suggests, it means that we have our fixed forms. They could be steel, they could be plywood. We lay down our forms, and then a large concrete truck comes, it pours concrete, and then a person, one of the construction workers, has to then go and screed it and make sure it's at the correct grade, etc. That's one option. The other option is called slip form paving. And in slip form paving, we do not have forms which are fixed. Instead, we have a very large machine which has forms on the sides, and a very low slump concrete is extruded through the machine. And as the machine moves forward, the forms move along with it, hence the name slip form. Regardless of whether we use fixed form paving or slip form paving, in both cases, we have to go back after the concrete is laid and after what's called the initial setting time. We talked about setting and etringite formation briefly in one of the earlier lectures in module 1. So at the point when initial set has happened, we need to go in and physically with a saw these joints. These are transverse joints or longitudinal joints. They have to be physically sawed in. Now, I should re-emphasize that this is mainly done for highways. For smaller applications, for example, if it's just pedestrian walkways or footpaths, it's also possible that you first put in what are called steel or aluminum, steel, or glass slats. So let me write that down. Slats. So they're just thin strips of aluminum or glass or steel. They are put in as sort of makeshift forms, and then concrete is poured in between them. So there we actually have a physical joint which you're placing beforehand. The key for that is that also becomes a very slow process because laying down those slats is fairly time consuming. So it's okay for small applications such as pedestrian walkways. Generally is not good enough for highways. So we don't opt for that solution for highways. So joints are generally sawed after casting. Now, when they are sawed approximately to a depth of h over 2. So if I draw a cross section, if this is my initial slab, then using a saw, I will actually saw a hole, which is our joint, but not the entire way. We saw it to a depth of h over 2. It is very important that this is done at the proper time. That is, this is done after the initial set time, so that once this soft cut forms, then as the concrete continues to harden, a crack forms below that. Remember, the purpose of putting the joint is to separate the two slabs. So we want to make these two physically two different pieces. They might have some interaction between them, which is also something we'll talk about later today. But we want to physically break the slab into two slabs. So we cut it into half, but it has to be timed in such a way that this crack forms below it, and the crack then propagates to the rest of the depth, and that's how the two parts of the slab are separated into two separate slabs. And finally, after that process is done, the joint needs to be sealed. And that's basically to prevent moisture ingress. So that's the entire process for construction. There is one exception to the sawing part, which is construction joints. That in case we're in a situation where the day has ended and construction has to finish for that day, then we just leave the joint as is, and the next day construction begins from that point onwards. So that's where we haven't sawed the joint. It's just there because we happen to leave it there at the end of the day. So those are construction joints, but those tend to be very few. The vast majority of joints are going to be these so-called expansion and contraction joints, which are the ones that we actually saw in. Okay, now, as I had mentioned, ideally we would like our slabs to be very small. The smaller the slab, the lower the stress. But the smaller the slab, the more amount of sawing which is required. That gets more expensive. You need more labor, you need more equipment. Remember, the sawing has to be done at a proper time. If it's sawed too late or if it's sawed too early, then that crack at the bottom will not form and you won't have complete separation between the two slabs. So if you want to saw a lot of joints, it doesn't mean you can do it in your own sweet time. It means that you need to get more labor, you need to get more equipment so that all of them can be sawed at the appropriate time and the speed of construction doesn't slow down. Therefore, we have to find some type of a balance between the size of the slab and the number of sockets that we have to make. If you have a very large slab, our stresses will be too high. If our stresses are high, then to counter that, we might have to have large thicknesses in order to reduce the stresses. Or if we have very small slabs, then our stresses are low, even if the thickness is low, but it's too expensive to construct. As a result, from experience, from really decades of experience, what has been found is slabs are generally 3.5 to 4.5 meters in width. Now, that is a general practice, but something to keep in mind that if you actually use, say, Westergaard solutions or any other set of solutions and calculate for 3.5 to 4.5 meter width for some typical load, if you calculate what is the actual stress, it's actually quite high in that case. Now, as a reminder, what we saw last time, we used Westergaard solutions and we got a stress ratio. So I remind you, stress ratio was the critical stress divided by FCR, which is the strength, which is the strength under flexure. So we saw previously that this stress was maybe around 45% or so, 44, 45% of the flexural strength. That's still a high number. It's less than 1, so it's still useful. It's still something that we can work with. It hasn't failed, but it's actually still quite high relevant to what we expect to get when we analyze rigid pavements. So really, this 3.5 to 4.5 meter, which is still a relatively large length or large width, makes one assumption that sufficient load transfer is available. And what is load transfer? Load transfer basically means I've got this picture over here where I've got a slab. I got this picture from Pavement Interactive. So I've got the slab. You'll see that around to h over 3 to h over 2, a saw has been cut. And if you look carefully, as I'm highlighting over here, that crack has formed underneath that. So that's why these two slabs have been physically separated from each other. So what load transfer means is that if I have one slab that my load is on, this slab is generally called the approach slab, as I'm writing over here. And the load, of course, is going to travel from the approach slab to the adjacent slab, which is what we call the leaf slab. So when the load is applied on the approach slab, we expect some amount of deflection to occur on the adjacent slab or the leaf slab as well. This is just a different way of saying that although the load is applied on the approach slab, a part of the load gets transferred to the leaf slab, which is why it undergoes some amount of deformation and some stress forms over there. This process is what we call load transfer. So to formally define it, load transfer is the transfer of a part of the load from the approach slab to the leaf slab. What the reason we want load transfer is, if two adjacent slabs are sharing a load, then individually each slab has a lower stress on it. And when each slab has a lower stress on it, they can be thinner and or longer. So the reason we can get away with having still relatively large slabs of 3.5 to 4.5 meters is because we do assume some amount of load transfer. So the next obvious question is, what are the different sources of load transfer? There are primarily three sources, which I'll actually explain in more detail in the next slide, but let me list them out over here. Those are base friction, aggregate interlock, and dowel action. So let me go to the next slide to give you an example of what these mean. So here again, I've got a slab, a little bit exaggerated in size, obviously. I've got a slab, a joint has been cut. The width of opening of the joint is called the joint width. Generally, it is of the order of 1 to 2 millimeters. And that's also a number that you should be familiar with. So as a pavement engineer, you should have somewhat of an idea of what a general slab width is. So it's around 1 to 2 millimeters in most conditions. So as I said, the slab which is loaded is called the approach slab, and the slab which is unloaded is called the leaf slab. When some amount of loading happens on the approach slab, then we'll have some displacement on the leaf slab side also. And that's what we call load transfer. The mechanisms of load transfer are as follows. The first one which I had mentioned was base friction. So now consider the fact that we have this slab. Now the slab itself is most likely, as we talked about in most cases, it's on a base layer. It can be an aggregate base layer, or it could be a cemented base layer, but it's on a base layer. So now if you imagine that this approach slab has deflected, I'm showing a very, very exaggerated view over here, but if the approach slab has deflected, then you can imagine the base is also being deflected, the base is also being pushed down somewhat. But because the base is monolithic, so the base does not have joints in it. That's an important consideration. Because the base does not have joints in it, and due to internal friction in the base, that could be internal friction due to aggregate interlock, or could be internal friction due to the cement, due to the fact that you have cement and therefore it's one monolithic layer. Due to that internal friction, the base layer also gets deflected. When the base layer gets deflected, then the leaf slab, because of its self weight, also gets deflected, because it essentially tries to follow gravity and it falls down. And so through the base layer, a small amount of load, we'll see how much in terms of quantities later in today's lecture, but a small amount of load gets transferred from the approach slab through the leaf to the leaf slab through this mechanism. An additional mechanism is what I showed over here, this aggregate interlock. So below about h/2 depth, this crack has formed underneath. Now, the crack has successfully physically separated the two. So if the two slabs are, for example, contracting, so I'll draw it over here, if the two slabs are contracting, then this crack is not going to offer any resistance to the contraction. So they can freely expand or contract, which essentially proves that they're two independent slabs. But what happens is, as you can imagine, because this crack is not a smooth crack, so it's somewhat of a twisty and winding crack, the aggregates inside the concrete are still in contact with each other. Maybe they don't offer any resistance during contraction, but as you can imagine, if the slab is bending, as I've shown over here, when the slab is bending, the left side or the approach side of the crack is going to pull down the leaf side of the crack, because the aggregates within the concrete are still in interlock with each other. And so this approach slab will end up pulling down the leaf slab because of this aggregate interlock. So the two mechanisms which I showed in this slide are the base transfer, transfer through the base friction, as well as transfer through aggregate interlock. There is one more mechanism which I put in this slide over here, which is dowel action. That is essentially that we place a dowel bar in between. We'll talk a little more about that in subsequent slides. But let's talk a little bit more first about load transfer itself. So now I've established that ideally, and this is true in almost all cases, we do have some amount of load which is being transferred from the approach slab to the leaf slab. The question is, how can we quantify this, or how can we measure this load value out in the field? For that, we define a new term which we call the load transfer efficiency, or LTE. The reason we define a term called LTE is basically it's a good measure of how much load transfer is taking place. As the name suggests, is some type of efficiency of load transfer. Furthermore, it's also possible, depending on the definition of LTE being used, and we'll introduce certain definitions in a few minutes. Depending on the definition of LTE being used, the load transfer can actually be measured directly in the field. Okay, let's see what we mean. So, for example, the picture I have over here, this is again of a two slab system. And if you assume the traffic is going in this direction, this black circle I have over here, that is the load. So it's moving from left to right in this diagram. And so naturally, this slab over here, this is the approach slab, and this is the leaf slab. Because the load is on the approach slab, as we established in the previous slide, the approach slab is going to cause some deflection, and a part of that deflection will also be transferred onto the leaf slab. So if there is a particular instrument which we call a falling weight deflectometer, we won't go into a lot of detail on it. It's a very, very useful instrument, particularly for something called pavement rehabilitation. We were trying to assess the condition of an existing pavement, not design a new pavement, but assess the condition of an existing pavement. This falling weight deflectometer, or FWD, as sometimes it's written as, it's a very commonly used instrument. It's also very useful. But as the name suggests, it's a falling weight. So we drop some weight. Maybe it's this black circle over here. We drop some weight, which is pre-calibrated. It has a certain diameter. It has a certain quantity, a certain value. So we won't talk about what it is. It's not important in this discussion. But we have this falling weight, and it's a deflectometer, so it's measuring deflection. So we have certain things called geophones attached to it. They're basically just tiny little instruments which are able to measure what is the deflection at the surface. So what we do is we'll put the falling weight deflectometer at the edge like this, and we have a geophone at the approach slab, and we have a geophone at the leaf slab. So at the point when the weight falls and causes deflection in the approach slab, we are able to successfully measure the deflection in the approach slab as well as in the leaf slab. So let me define the deflection on the approach slab as dA, which I've highlighted here, and the deflection on the leaf slab as dL. Again, these are values that can be measured. So the geophone will essentially just give you this value. We then formally define load transfer efficiency using this formula. So LTE is always shown in the form of a percentage. It is dL over dA into 100%. So again, dL is the deflection on the leaf slab side, and dA is the deflection on the approach slab side. Now, this is one of three possible definitions of LTE. I'll show you other definitions in coming slides, but this is actually the most common definition as well, which is why I've brought it up first. So let's ask a question just about this formula. If I say that this LTE value is 0, what does that mean? Well, if I'm saying dL over dA is equal to 0, I'm basically saying dL is equal to 0. Again, just to draw out what's going on. So I have this approach slab. So I've got the approach slab over here, which is A. I've got the leaf slab over here. Some load has been applied onto the approach slab. The approach slab is definitely going to deflect because the load has been applied to it. If dL is 0, that means if the deflection of the leaf slab is 0, that means the leaf slab is not participating at all in the load transfer process. There is a finite deflection in the approach slab, dA, but the deflection in the leaf slab is 0, which is to say that dL is equal to 0, which is to say load transfer efficiency is equal to 0, which means that there is no load transfer. The leaf slab is not playing a role in this process. This is actually quite a bad case. You don't want such a situation to happen. And in general, this sort of situation will not happen in practice. In practice, you'll have at least a little bit of load transfer. And we'll see about sources of load transfer in a couple of slides. Now, the opposite here, what does it mean that load transfer is equal to 100%? Well, going back to this formula, what that basically means is dL is equal to dA. I hope you can prove that. So it's like dL over dA is equal to 1. So dL is equal to dA. What that means is if I have some amount of deflection on my approach slab, I get exactly the same amount of deflection on my leaf slab, which means how much of a load my approach slab is withstanding, the same amount of load the leaf slab is withstanding. So I've taken what my external load and I've perfectly divided it 50-50 in between the two slabs. That's a very ideal situation. It's very rare actually to have an LTE of 100%. In physical terms, it doesn't really mean anything because it almost never happens. But it is possible for us to get an LTE very close to 100% if we use double bars, which we'll talk about in later in today's lecture. So that's the basic definition of load transfer efficiency. As I mentioned, there is also an alternative definition, and it's sometimes useful depending on the application. And the formula I have over here is here. Again, it's based on the deflection of the approach slab and the leaf slab. So if this is my approach slab, right? So I've cut the joint and then I've got a little I've got a socket up here and then I've got a little crack below that. So now if this is my approach slab and this is my leaf slab and my load is going from approach to leaf slab. So the approach slab is loaded. It has a deflection which can be measured using a geophone of dA. And then the leaf slab has some other deflection of dL. This definition of LT up here is basically the ratio of the deflection of the leaf slab to the average deflection of the two slabs. So the previous definition was the ratio of the leaf slab to the approach slab. This is the ratio of the leaf slab to the average deflection of the two slabs. So it's two. This is actually to be read as DL over DA over DL over 2. That's why this 2 is coming in the numerator. So then let's ask ourselves the question in this case, what does it mean to say that LTE is equal to 0%? Well, if LTE is 0%, this is a fairly straightforward calculation. It still means that DL is equal to 0. That means we have some amount of deflection in our approach slab, but the leaf slab is not participating at all in that process. And the other method, the other measure we have is what if this, in this definition, LTE is equal to 100%? Well, let's look at that calculation. What that is saying is 2DL is equal to DA plus DL. DL cancels out. So that's simply DL is equal to DA, which is actually exactly the same situation we had previously. That if you look at the previous definition, 100% also meant DL is equal to DA. So here also 100% means DL is equal to DA, which means whatever deflection is occurring on the approach slab, exactly the same deflection occurs on the load slab. So there's a complete and perfect transfer of load. Both slabs are now bearing exactly the same quantity of load. So that is a situation when in this definition, LT is equal to 100%. Now, values in between don't have the same interpretation. So as I said, LT is equal to 0 is very unlikely. LT is equal to 100 is also very unlikely. Values in between, the interpretation of those values between these two definitions of LTE vary. But I will leave it to you to try to figure out what would that interpretation be. Again, it's used in, depending on the application, different definitions are used. But the first definition I put over here is the most important definition, which you will find mostly used in the literature. So that's what it means to be able to have load transfer. Now, I've got an example here. Before the example, though, I just want to show one more definition. There is a third definition of load transfer efficiency. Now, I should say this definition is not widely used in practice, and I'll explain why in a second. This definition, unlike the previous definition, which is based on deflection, this definition is actually based on peak tensile stresses in the leaf slab as well as in the approach slab. So this is a stress-based definition. And as you can imagine, LTE in this case is the stress developed in the leaf slab divided by stress developed in the approach slab into 100%, where by stress, I mean the peak tensile stress, or what we can call the critical stress. Now, what is obvious about this, that this is based on stress, and stress is not something that we can directly measure in the field. Unlike deflection, which we have geophones, we have actual instruments that can measure it, stress is not something that can be directly measured in the field. So this definition is not something you can actually use in, say, pavement rehabilitation, because you can't measure this value directly. It is rarely used, this particular definition, but it may be useful in design. So when you're doing design, for example, when you're using Westergaard's theory and you're calculating stresses, and then you're interested in accounting for load transfer, in such a situation, you might be particularly interested in using a stress-based definition or maybe even a load-based definition. Indeed, when we go into little more detail on analysis of dowels or dowel systems, we will see this sort of a definition coming back. But beyond that, beyond design applications, and even that is not used too much anymore as we've gone to using finite element methods, but beyond design applications, this equation is not particularly useful. Okay, so with that, we've seen three definitions of load transfer, two which are based on displacement, of which the first one is the single most commonly used definition of load transfer efficiency, and a third which is based on stress, which might be used in some stress analysis, but it's not commonly used. What we'll do now is I want to quickly go through an example and demonstrate how to do these calculations given some amount of data. All right, so let's look at this example. It's a relatively easy example, but I hope it illustrates how simple this calculation is. So suppose an FWD load is applied on the approach slab and the deflection is measured at a distance of 50 mm from the edge is 0.02 mm. Now, the deflection at the corresponding point on the leaf slab is 0.017 mm. Calculate the LTE based on the two deflection based definitions. So what we have here is we have the two slabs. So again, the joint is like this that we saw up to about h/2, and then below that we allow this crack to propagate. So here we let's say that this is the approach slab, and let's say that this is the leaf slab. What it says is that some FWD load has been applied, perhaps over here. It doesn't exactly say where it's been applied, so we'll go with the assumption that the load is somewhere close to the edge. So the load has been applied, and at some distance 50 mm from the joint, the deflection has been measured on the approach slab, and a similar distance 50 mm deflection has been measured on the leaf slab. We are given, if you look at our data, DL is equal to 0.017 mm and DA is equal to 0.020 mm. Now, one thing to notice, it's obvious, but it needs to be stated, DA is going to be greater than DL. So DA is the actual loaded slab. So the slab which has the load, well, it's greater than or equal to the DA the slab which has the load is the one that's going to have the higher deflection. At most, the next slab will have the same deflection. It's physically not a possibility for the leaf slab, which is not loaded, to have a higher deflection than the approach slab. If that happens to be the case in the measurement, then either there's some issue with the instrument, or there's some other effect going on, something to do with the base, something to do with the material, and that's something that has to be investigated. But if everything is correct, then DA is always going to be greater than or equal to DL. So we're given this data, DL and DA. We are asked to calculate the LTE based on both definitions. So as I previously pointed out, in the first definition, which is the easiest definition, LTE is equal to DL over DA into 100. And I'll show the calculation in the next slide. But that's basically going to be 0.017 into 0.020 into 100. Again, I'll show the definition. The second definition of LTE is basically DL over, let me call it the average of DA and DL. DA and DL. So we have to calculate the average of these two first. So that's going to be 0.017 plus 0.02 divided by 2. We'll do that calculation. And then that's plugged into this value where DL is 0.017. Now, if you just think about it previously, in our previous slide, we said that if LT is equal to 0 or LT is equal to 100, for both the formulas, they essentially mean the same thing in terms of what measurement of deflection you'll be getting. Is that the case also for values in between? Well, let's look at the solutions. Based on our first definition of LTE, we calculate that the load transfer efficiency in this case works out to 85%. But based on our second definition, which is based on the average deflection, it actually works out to 91.9%. So the two values are not the same thing. A question which you may want to try on your own is that if I actually plot DA and DL for different values of LTE, so if I have some kind of contour for different values of LTE, then which of these two definitions of LTE increases faster as DL starts approaching DA? Both will eventually land up at 100%, but which one gets to 100% first? Presumably it's the second value, but again, that's something I will let you do the calculation for and figure out yourself. Okay, now we already talked about the first definition of load transfer. All right, so now that we've established what is load transfer efficiency, how do we measure it, what are some different definitions of it, what I want to talk about is what is a realistic load transfer efficiency that you can expect in the field. Now, as I previously mentioned, there are basically three sources of load transfer. The first was base friction, which is essentially because the base is a monolithic layer. So as the approach slab is deflecting, the base deflects. As it's monolithic, it also deflects underneath the leaf slab, and then the leaf slab also deflects. This is almost always going to be present. Regardless of whether we have an aggregate base or a cement-treated base, you will almost always have some amount of base friction. But if we had just base friction and no other value, that is, for example, if this was my approach slab and this was my leaf slab, and I ensured that the joint went all the way through, that there is no aggregate interlock, and then if you actually measure the typical LTE, it has been found that that works to around 10%. It's a pretty small value if you think about it. It's really not enough to justify having a slab as long as 3.5 to 4.5 meters. Fortunately, this is not how joints are made. Joints are sawed only up to H/2, and then we allow the crack to form in between. This crack is where aggregate interlock is created within the joint. So if the joint has been sawed properly, then we will have some amount of aggregate interlock, and that aggregate interlock will then increase our load transfer efficiency to about 50%. I want to point out, I'm not saying that if you don't have base friction and if you have only aggregate interlock, then LT is around 50%. You will basically always have base friction. It's impossible to eliminate base friction. It's possible to eliminate aggregate interlock by sawing the joint all the way through. It's also possible to eliminate the next factor, which is dowel action, by essentially not putting a dowel, but it's not possible to eliminate base friction. So what you're looking at this 50% is the combined effect of base friction and aggregate interlock will give you around 50%. And finally, we have dowel action. So dowel action is when, in addition to having the base friction, in addition to having aggregate interlock, we actually put a steel bar, which is called a dowel. We actually physically put a steel bar inside the joint, and then that steel bar, additionally, when this approach slab is started to deflect, the steel bar also deflects, but then it starts pulling down the leaf slab along with it. That's basically what we call a dowel, and that action of this dowel first being pulled down by the approach slab, and then the dowel pulling down the leaf slab and therefore creating load transfer, that entire action is called dowel action. Of course, it's not necessary that you have dowel action. You only have it in case you have physically applied dowels in JPCP, which is quite an economic consideration also because steel is not inexpensive. In that case, if these conditions are satisfied, that you have base friction, which you almost always have, if you have aggregate interlock, which a well-constructed pavement will have, and if you have added a dowel in addition, then the total load transfer efficiency will work out to 90%, which is very high. Can it be 100%? Generally, no, you won't get 100%, but it could be higher than 90% initially. Over time, the load transfer efficiency increases. The load transfer efficiency decreases over time. And we'll talk about why that is the case when we get into some of the analysis. But over time, it does decrease. But on average, it's safe to assume that with dowels, the combined load transfer efficiency is 100%. So this formula I have over here, this is actually for what I call just defined as the combined or the composite load transfer efficiency. If somehow I could measure the load transfer efficiency using each of these phenomena, that is through the base layer, the base friction, through aggregate interlock, as well as through dowel action, if I could somehow measure them individually, then I would get the composite one as the product of, and this is a relatively simple formula to prove. I'm not going to prove it, but it comes from fairly simple considerations of load transfer. So it's basically the combined 100 minus of the combined LTE divided by 100 is 1 minus LTE of each type of load transfer, the product of that. So product of 1 minus LTE of each mechanism gives you 1 minus the composite or the combined LTE, and from that we can calculate the combined LTE. So these values which I've put up here, LTE of 10%, 50%, 90%, these are these combined LTE values. And through the formula which I've shown over here, that's how they are related to the base, aggregate, and dowel action load transfer efficiencies. Okay, let's talk a little bit more about dowels. These are very important components in JPCP. They're also going to form the basis of the next two lectures that we will also cover. So we should know a little bit about what they are and how they act. So dowels are basically steel bars. They may be corrugated steel. So corrugated steel basically means they have these rib structures on the surface. They may be corrugated or they may be non-corrugated. As we shall see, unlike, say, structural engineering, where we basically always want corrugated steel because we want good bond between the concrete and the steel, in some cases for pavement engineering, we actually don't want a very good bond. I know that sounds counterintuitive. We'll see a little bit more about it in the next lecture. But in some cases, we actually don't want the steel to be corrugated. We don't want good bond between the concrete and the steel. So we do have the option of also using non-corrugated steel. The dowel bars are placed at a depth of H/2. So after the load pavement is cast, we cut it to H/2. In terms of construction, what we actually do is we first lay out a bed of these dowel bars. So on what we call a chair. So if this is a dowel bar, we actually put it on a very thin, somewhat flimsy metallic structure called a chair. Let me write that down. So this is called a chair. We put it on a chair. We lay it out at whatever appropriate locations where we expect joints to be sawed. and then we pour concrete over that. So the concrete covers this entire dowel, and then we saw up to a depth of h/2, such that below that a crack would form later. So this depth of h/2 is where we place the dowel in the case of JPCB pavements. I want to point out that this should be compared to reinforced concrete, which all of you have studied in structural engineering applications. In structural engineering applications, you learned that the steel is actually placed on the tension side. So that could be on the upper side in case of, for example, a cantilever beam. It could be on the lower side in case of, say, a simply supported beam. But in jointed plain concrete pavements, the purpose of dowels is actually not to resist tension. The purpose is to perform load transfer. And that load transfer mechanism is most efficient if the dowel is placed at this depth of h/2. Also, as you shall see a couple of lectures later, we'll see that the tension side and the compression side of a rigid pavement keeps changing during the day. So depending on whether it's day or night, different sides have tension and different sides have compression. So we don't have a unique tension and compression side. So we can't actually just put the steel on the tension side. Okay, so how does dowel action work? I have this diagram here on the right. So again, if this is the approach slab, which I'm writing with A over here, and this is the leaf slab, and the approach slab is loaded, because the approach slab is loaded, the slab is going to deflect, as I've shown here. Now, as the slab deflects, we have this dowel bar which is bonded to the approach side. So the dowel bar is bonded to the approach side, and then because it's bonded, as the slab deflects, the dowel bar deflects with it. So this whole thing monolithically deflects downwards. Now, because it deflects downwards, what happens is that this dowel bar on the leaf slab side, so the dowel bar, half of it is on the approach slab side, half is on the leaf slab side. The dowel bar on the leaf slab side, that because it's essentially the same dowel bar as on the approach slab side, that also is pushed downward. Because it's pushed downwards, it pulls the leaf slab along with it downwards. So that's the load transfer is happening from the concrete part of the approach slab through the bonding between the concrete and the dowel to the dowel on the approach slab, from the dowel on the approach side to the dowel on the leaf side, because it's basically the same physical dowel. And then the dowel on the leaf side is pulling down the slab on the leaf side. So that is the entire mechanism of dowel action for performing load transfer through dowels. So to put it in a slightly different way, but it essentially means the same thing, dowel bars transfer loads during bending. So only when we have this type of bending action do dowel bars transfer load. But as I'm sure all of you are aware, and we had discussed this earlier also, slabs tend to expand and contract depending on temperature. Now, several lectures later, when we talk about climate effects, we will go into very detailed explanation of how we can analyze temperature effects. But for now, it's sufficient to understand that if you have a slab, if it's a hot day, it's going to expand. If it's a cool day or a cool night, the slab is going to contract. So what we want is during the process of expansion and contraction, when the two slabs are sharing a dowel, during this process of either expanding or contracting, we don't want any resistance to expansion or contraction. If we have any resistance to expansion or contraction, then we are going to develop stresses, and stresses can eventually lead to cracks depending on their magnitude. What we want is that, for example, if the two slabs are undergoing compression, we want them to be freely able to undergo compression without any resistance, which means we want the dowel to easily slip from one side to the other. So again, when the slab is undergoing bending, we want a load transfer. But when the slab is undergoing compression or expansion, we don't want any load transfer. We simply want the slabs to freely undergo expansion or contraction. Therefore, in addition to enabling load transfer through bending, dowels must also allow free expansion and contraction. How is this possible? This is basically achieved by coating one side of the dowel bar in epoxy. As I had said previously, ideally dowel bars could be corrugated or non-corrugated. It is okay if they're non-corrugated, because if they're non-corrugated, it means they're not going to have too much of a bond with the slab on the other side. So for example, if this is the leaf slab and we choose this side to be non-corrugated, then there's not going to be too much of a bond between the concrete and the slab, so it becomes relatively free to move. In addition, when you cover it in epoxy is a certain chemical. It's sort of like an adhesive which becomes solid after a couple of times, and there are other ways to enhance that process and increase the strength. So epoxy tends to be green in color, if any of you have seen it. So this image I have over here, we have dowels which are bonded to one side of the slab. The other side of the slab, however, the dowels have been covered in epoxy. So that when we pour concrete over this and then this is covered in a slab, because of the presence of epoxy, there's going to be very little bond. It's essentially going to be a very smooth surface. And so there's going to be very little bonding between the concrete slab and the epoxy covered dowel. That is what's going to allow free expansion and contraction between the two slabs. So the slab is properly bonded on one side, and we want it to be, to the maximum extent possible, we want it to be unbonded to the other side. That's how we achieve this free expansion and contraction. Regardless of the extent of bonding, however, we are basically always going to have this load transfer through bending. Okay, now, so that was all about dowels, but that was dowels actually on transverse joints. So let's talk a little bit about another type of joint, which is called a longitudinal joint. To explain this, it's actually best if I show this diagram, or actually let me just draw a separate diagram. So previously I had defined that the direction in which the traffic goes, we call this the longitudinal direction. And the direction perpendicular to it, we call it the transverse direction, which I've written as long in trans over here. So now, here is my system of JPCP slabs with that definition of longitudinal and transverse joints. So I've drawn a series of JPCP slabs. Now, what happens is that we usually put dowels on the transverse joints. So these joints are going perpendicular to the direction of traffic. So these are the joints which are called transverse joints. So we might put dowels over here to ensure load transfer efficiency. Of course, as you can imagine, the size of this joint which I showed is highly exaggerated. It's just 1 to 2 millimeters. It's just for illustration. So these are called transverse joints. These are in the direction, these are perpendicular to the direction of traffic. But then we also have these joints over here, which are parallel to the direction of traffic. Those are called what we call as longitudinal joints, which I've written over here. What happens is, what happens with these joints, therefore, is in between these, we can also put steel. It's not that steel cannot be applied over there. And it's not that those steel bars do not cause any load transfer. They actually do. It's just that we may not consider it in our analysis. It's not particularly important during the analysis to consider dowel bars, to consider these bars in between. So, as an illustration, let me show this as a better picture which I drew up before I started the lecture. That here again, this is our direction of the traffic, and so across the transverse joints, we've placed these dowel bars, which I've shown here in green. So this is in green. And in the longitudinal joints, I've shown the bars here in blue because of the fact that historically we assume load transfer is happening because of the dowel bars in the transverse direction or in between the transverse joints. But load transfer, we do not historically consider it in between the slabs along the longitudinal joint or across the longitudinal joint. So we consider this historically we consider this load transfer. Historically, we do not consider this load transfer. For that reason, we give a different name to these steel bars. We call those tie bars. Historically, the reason it's called tie bars is the idea is that these bars are tying the two sides of the slab together, but they are not participating in any load transfer. Now, I should add, I keep emphasizing this term historically is because this is not accurate. There is a load transfer. Because you got steel over here and the slab is going to undergo bending, well, the slab is going to bend along both directions, both the longitudinal and transverse directions. So there is actually going to be a load transfer in between. However, our analytical techniques, which we will actually see in the next two slides, our next two lectures, the analytical techniques we use to analyze this are not well developed for longitudinal joints, which is why for tie bars, we historically don't consider it. But as we shall see in module 3, when we get to the finite element method, that is a much more sophisticated method, and that does have the capability of considering load transfer along the longitudinal joint. So that's why I keep emphasizing the fact that this is a historical assumption that dowel bars participate in load transfer, but tie bars don't participate in load transfer. It's not mechanistically correct, and using modern tools, finite element method, we can correct for this. Now, one more thing which you see on this diagram is what I've written here in untied shoulder. So what we see here is we've got slabs along this direction, we've got slabs along here, and in between, along this longitudinal joint, these blue tie bars have been applied. At the end of the road, we actually have what's called a shoulder. Now, the shoulder is basically put in place, and I hope all of you studied this in your undergraduate courses. The shoulder exists not due to pavement engineering considerations, but due to traffic and economic considerations. We'll talk a little more about that as we go forward. But if we have a shoulder over here, and I've shown it in black over here to represent that this shoulder could be, for example, a flexible pavement. So it could be the bituminous section, which is the shoulder. In that case, we can't put any steel in between. So when you have an untied shoulder, it's called untied because we don't have any tie bars. And so based on modern analysis, no load transfer is happening between the slab and the shoulder. An alternative possibility is that our shoulder also consists of slabs. So basically, our shoulder is also a set of JPCP. Generally, the width is going to be smaller. This might be, let's say, 1 to 1.5 meters. So the width is going to be smaller than a typical slab. But in this case, here again, in green, I've shown here what are the dowel bars. So this is in green. I've shown dowel bars over here, and I've shown tie bars in blue. So in this case, we have tie bars along this longitudinal joint. That's the same thing as the previous case. But if our shoulder also consists of PCC slabs, then we also can put tie bars in between the what's called the travel lanes as well as the shoulder, in which case we call this a tied shoulder, that you have a tie bar which is between the shoulder and the actual travel lane. So again, to compare, when you do not have a dowel bar when you do not have a tie bar between the shoulder and the travel lane, and that's typically when the shoulder is made of a flexible pavement, we call that an untied shoulder. When the shoulder is made of also rigid pavements, it also consists of PCC slabs, then we can put these tie bars in between, and that's what we call a tied shoulder. In this case, in both cases, in classical analysis, the presence of the tie bar does not make a difference in terms of load transfer. But that's mechanistically not correct. In modern analysis, which we'll talk about in module 3, in modern analysis, we can incorporate the effect of load transfer in between across the longitudinal slab. So what's effectively happening is that if you have an untied shoulder, then you are not taking advantage of the fact that some amount of load can be transferred onto the shoulder. Whereas when you have a tight shoulder, you can account for a load transfer from the travel lane into the shoulder. And so you can decrease potentially the maximum stress on the travel lane. So that's the difference between a tight shoulder and an untied shoulder. Now, as I mentioned, the main reason we actually have shoulders is actually from a traffic engineering and to an extent also economic considerations. So why traffic engineering? Shoulders are basically added for safety. The idea being, although I know in India you'll find plenty of exceptions to this, but the idea being that you're not supposed to ordinarily travel on the shoulder. The shoulder is meant for emergency stop-off. So if you're driving on the road, you should not be stopping. And this is mainly meant for highways. But if you're driving on the road, you should not be stopping because then you'll be rear-ended by another vehicle. But if you have an emergency that for whatever reason you need to stop, you need to come off to the shoulder where vehicles are ordinarily not driving, and then you can stop there and deal with your emergency. So shoulders are provided for that reason. An additional reason that shoulders are provided is due to economic considerations. For example, due to whatever the cost works out today, it might be possible that you build a 4-lane highway. But over time, due to something we call latent demand, and again, that's something you should take a course on transportation economics for, we won't have time to go into here, but due to a phenomenon called latent demand, when you build a 4-lane highway, you will actually end up increasing the volume of traffic over time. So eventually that 4-lane highway, for example, is going to be inadequate. It's going to have a lower level of service, or vehicles are not going to be able to travel comfortably and speedily on it. So over time, you might have to expand it from a 4-lane to a 6-lane or maybe even an 8-lane highway. Transportation economics tells us that when you build a road, generally the land prices around that road are going to increase over time due to increased economic activity. And that's essentially been the case all over the world wherever there is decent economic activity. So the idea of having shoulders is, instead of building just a 4-lane highway, create shoulders. The shoulders are acting as emergency stop-off, but they also allow for future expansion. So you could potentially convert the shoulders in the future into new travel lanes, but the cost for acquiring the land is borne today when the land price is still relatively low. So those are two reasons, due to safety and economic reasons, why we have shoulders in the first place. And of course, as I mentioned, tight shoulders can also participate in load transfer, although in our classical analysis of load transfer, we don't take this phenomenon into account. When we get to modern analysis using the finite element method, we will be able to take this phenomenon into account. Okay, final two slides, I just want to briefly talk about joint maintenance. So, as I said previously, joints are basically holes which we've created in the pavement. Those holes create a means for moisture ingress. So, if we just have a joint as over here, so here we've cut the joint and then a crack has formed underneath. If water falls through the joint, it's possible that the water will eventually seep into the base layer, and eventually, over a decent amount of time, it will also seep into the subgrade. That's going to essentially weaken our foundation layers, and over time is going to cause a variety of distresses in the concrete. So it is very, very important that we seal the joint. And this image which I have over here essentially shows a joint sealant. A joint sealant is some type of an asphaltic product. So it's made of something which is a byproduct of the byproduct of crude oil. It's some type of a polymer material. It's not the same as bitumen, but it's some type of polymeric material nonetheless. So what we do is we just inject this sealant. It comes in a tube. We inject the sealant into the joint, and this is being polymeric, it is waterproof. So this waterproof sealant then prevents moisture from entering and getting into the base layer. However, one important aspect is that if we are pouring the sealant here, the sealant should stick properly to the walls of the joint. Now, on its own, the sealant, the way it is made, the way it is designed as a product, it is adhesive to concrete. The problem is that if after sawing the joint is not properly cleaned, then the sealant will not stick. Why is that the case? Because when we saw through the joint, we create a lot of dust. Any of you who've taken your basic classes in machining and you've done any sawing, you know it creates a lot of dust. So after you saw, a lot of dust is generated. If that dust is not cleaned before the sealant is applied, then actually you're getting adhesion between the sealant and the dust, not the concrete. And so then the dust, of course, is not attached to the concrete, so it can come off and the sealant will come off with it. So it's important that after the joint is been sawed, you have to use basically a vacuum cleaner. You have to use that, or you spray basically pressurized air on it. You spray air or use a vacuum cleaner kind of thing, and you get rid of the dust on it. After the dust is removed on it, then the sealant is applied. I should add, this is very important actually in Indian conditions, because India is a very dusty country in general, particularly out in rural areas where you're doing construction. So because it's a very dusty country, if dust is present in the joint at the time sealant is applied, then the sealant is going to degrade. What does it look like for a sealant to degrade? Here is an example. So here I've got a joint and a sealant has been applied. As you see, over time, the crack has opened up. Some amount of spalling is also happening around here, and so the sealant is becoming detached from the concrete. So in this case, the detachment could be because of improper construction. That means you had dust over there. It's also possible that it's occurred due to the fact that the crack is growing, and then the crack is basically becoming detached from the sealant. So there could be a variety of reasons. In this case, there is a need to periodically clean and reseal the sealant to prevent moisture ingress. So over time, you are certainly going to have some amount of deterioration in the sealant. It's important as part of pavement maintenance to inspect, see where you're having loss of sealant, clean that and reapply the sealant. If this is done on a regular basis and properly, then it's most likely the case that unless other issues don't exist in the topography, you're not going to have any moisture related problems, and so you'll be able to reduce the amount of cracking. Okay, so that was all about joints. We talked generally about the importance of joints, why we have joints, and joint maintenance, and we went into some detail on joint construction. What we'll do in the next lecture is we will talk specifically about dowels, because they are the most important load transfer mechanism when considering joints for JPCB pavements. We will look at dowels, and we'll in particular look at a theory called the Freiberg theory, where we will do some numerical analysis on dowels and see how we can measure the effectiveness of dowels. So that will be our discussion in the next lecture. Thank you.